Okay, let's go through. I guess I need a packet. Okay, so we've seen this data before. I wanted to use this specific example because you've seen this before in order to teach you the last thing that you need to learn for this unit. So this unit is all the correlation and regression, taking two variable data and figuring out like how closely they're related and using one variable to predict the value of another in a certain circumstance. So here we're dealing with heights of the father and their sons. So we're going to be possibly using the height of a dad to figure out how tall his son is going to be or is or whatever, okay? So the information that you have on your purple packet is that the average father is 68 inches tall. And the SD for the dads is 3 inches. Okay? And then the average son, or the average height of all the sons in the data, is 69 inches. And the SD there is 3.5. And then an R value of 0.71. What does this mean? Yeah, so is that a good correlation? It's decent, yeah. So 50% is like, or like a 0.5 is just middle. Like they're in between not correlated and perfectly correlated. So 0.7 is better than that. It's not great. Usually we expect like a 0.8 or something for a really close association or a really close correlation. But 0.7 isn't bad. So there seems to be some sort of positive relationship between father's heights and son's heights, which makes sense. The father, the taller the dad, it seems like the taller his boys would be. Yes? Seems logical. No matter how tall the wife is, if the dad is getting taller and taller and taller, then the sons will probably get taller and taller and taller, assuming the wife stays about the same. Okay. So the first question, what is the slope of the regression line that we can use to predict son's heights from father's heights? What is that formula for slope? And in this situation, what is X and what is Y? X is the father, and Y is the son. And can you explain to me why you think that's true? Yeah. So whichever one we are using is our X. That's going to be our input. Whatever one we're trying to predict is our Y, which is our output. Good? Okay. All right. So slope, we're going to plug some numbers into here. So we'll get a 0.71 times, what's SDY? 3.5 divided by SDX, which is 3. Throw that in a calculator. What do you get? Okay. So if the slope is 0.828, now interpret the slope for me. What am I asking you to do there when I say interpret the slope? What does that mean? Okay. Was that what you were going to say? So basically, for every additional inch of height on the father, we expect 0.82 inches of additional height on the son. Does that make sense to everybody? Okay, do I need to write that down, or did you already write that? So for every additional inch of height on the father, we expect 0.82 or 0.83 inches of additional height on the son. So if you've got a dad that's 68 inches tall and a dad that's 69 inches tall, if the son of the 68-inch dad is also 68 inches, we only expect the height of the other son to be 68.83 inches, not a full 69 inches. Yeah? Okay. All right, so there's our interpretation of the slope. Now we need to find the y-intercept. Suggestions for how we might go about doing this? Good. So we have two options here, and if you look at your formulas page right after slope, there are two options for the equation of the line. If you find the equation of the line, you have found the slope. Okay? So you can use y equals mx plus b and actually think about the calculation finding the y-intercept. Or you could use the point slope form, that second option, and when you're done rearranging it, your y-intercept is in there. So it doesn't matter. Okay? I've grown quite fond of the point slope form. I'm actually quite sick of the y equals mx plus b, but I know a lot of you use that way, so I'll do that way first. So if I want to use y equals mx plus b to find the y-intercept, then I need to plug in m. What's m? The 0.828. What do I put for x and y? The average and the average. So x average, 68. Y average, 69. Okay? How do I solve that? How do I find b? How? Do I divide? Please say no. I subtract. I'm trying to get b by itself, and that number, that whatever, 0.828 times 68, that is being added to b. So to get rid of it, I subtract that from both sides. So I get 12.696. Okay? It's okay if you don't round to 3 digits when you do it. It's fine. Just want it to be thorough. Is that your y-intercept? Yes. Can you interpret that number? That's a little tricky. Yes. So if your dad is 0 inches tall, you're going to be about 12.7 inches tall. So the question on the purple worksheet is, does the y-intercept make sense in the context of this data? Do you think we collected data from fathers that were 0 inches tall? No. All right, part E, what is the equation of the regression line? Most important thing you will do in this entire unit. What is the equation of the regression line? Go. Okay. On a scale from thumbs up to thumbs down, how are you feeling about your ability to take that data and get to this point? Thumbs up, I know I can do it. Thumbs down, I have no idea what you're talking about. You're definitely speaking a foreign language. And somewhere in between. Okay. So, friendly reminder that you have to do math on the days that you're not here. Sorry about it. Okay? So, just keep you have to, like, this is not something that you can just hop in every 3 weeks and learn. It's not going to work. Okay, so please, 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 from this point forward, make sure if it's an 8A, you're doing math. There will be something posted for you to do on Canvas. Make sure you are doing it so that we stay caught up. When January comes, that's when we start our official UVU course. That's when we will be taking the tests that count on your UVU transcript, on your college grade. I'm pretty nice when it comes to your high school grade. I will do a lot to cushion that. I can't cushion your UVU grade. Okay? And this right here, the stuff we've done leading up to this, and this, what we're doing right now, these are the fundamental pieces. If you have these down, the rest of what we have to learn this year is pretty easy, pretty straightforward. But if you don't understand this basis, it's going to be a long, miserable road. Okay. All right, what's next? Use the regression line to predict the height of a son given that his father is 72 inches tall. How do I do that? I just plug it into the equation, okay? That is the point of the regression line. Sam, are you with me? You got lots to learn today, friend. That is the point of this line. The point of this line is to take this data, okay, where we had a bunch of father-son pairs and we collected their heights. That regression line is going to basically summarize that data for us so that we don't have to talk about each individual dot. We can just say, it's about here. Yeah? So now I can take the height of a father and make a prediction about how tall his son is going to be or how tall his son already is. Okay? How accurate will it be? Do me a favor, plug in 0.71 times 0.71 into your calculator, or do 0.71 squared. Okay, so about 50% of the time, this equation is going to give us a pretty accurate guess for the son's height based on the father's. Half of the time. It's not great, okay, but it's better. Didn't we have one the other day that was like 11% of the time it was going to be a good guess? So 50% is a little better. I'll take it, okay? All right, so we are going to make a prediction about the son's height given that the father is 72 inches tall. How exactly do I do that? Plug it in. So the father is 72 inches. The son is predicted to be 0.828 times 72 plus 12.696. What did I just do? Okay. I got 72.312. So we guess that if the dad is 72 inches, we predict that his son will be what? Just a tiny bit taller, right? Tiny bit. Okay? All right. Any questions up till there? Is there a part that I need to go back and review? I really want to make sure you're solid on that stuff that we learned over the past couple of weeks because now it's time. Now it's time. The one new thing. Okay? It really is something you've already done before, but wrapping your head around how it works is going to be a little bit tricky. Okay? All right, so any questions? We got slope, we got writing the equation of the line, we got plugging it in. Good? Okay. So, part G, we actually talked about last week. How much error is there associated with your estimate in part G? That's your RMS error. So on your formulas page, you have a formula for RMS error. Now, remember, there are two different types of RMS error. Sometimes my RMS error is this number right here. Do you remember that? And sometimes you use the formula on your page. Can you tell me when you use this and when you use that formula? Yeah. If I have no information, if they didn't tell me, hey, the dad is 72 inches, if I have no information, if a kid just says, hey, how tall do you think I am? I was in that data set. And I say, how tall is your dad? And he says, I'm not telling you. And I say, okay, well, I have no information, so I'm just going to guess that you must be 69 inches tall. I have no other information. If I just guess you must be about 69 inches tall, my give or take on that guess, or my error, how far off I'm expected to be, is 3.5 inches. Okay? Now, does it make sense that that number should go down if I know how tall his dad is? Yeah, you should be able to make a more accurate guess about the height of a son if you know how tall his biological father is. True? Okay. So the error on that guess is that formula on your formulas page, the RMS error, which is that SDY, that same 3.5 we just talked about, but then multiplied by the square root of 1 minus r squared. So it's 3.5 times the square root of 1 minus 0.71 squared. This will be our new give or take. Did you get 2.46? Okay, cool. Okay, so how does 2.46 compare to 3.5? Yeah, it's a little more accurate. I expect my guess of this kid's height to be more accurate because he told me how tall his dad was. Okay, so instead of saying give or take 3.5 inches, I can say give or take 2.5 inches and feel pretty good about that estimate. So we anticipate that this kid is 72.3 inches tall with this much error on that guess. Okay, now those two numbers right there actually define the normal distribution for the heights of sons, all the sons that have a dad 72 inches tall. So look at on the front, look at the data, look at this tape or this scatter plot right here. Thanks. Abby, Sarah, and Kaysen, they're all when convenient, so it's something to do with NHS. Okay, so do you remember, I don't know if you remember when we talked about this data before, but there's a chimney at 72 inches. Yeah? And that contains all of the pairs of father and son that have a dad that's 72 inches tall. Okay? Are all of the dots in there located at 72.3 inches? No, there's like maybe one dot at 72.3 inches. Okay? But would you say, so the dashed line that goes on the diagonal, that would hit through there at exactly 72 inches. Okay, so do you see how there's a couple dots just right above it that we could maybe say are close to 72.3 inches? But really, there's a lot of other points, right? Would you say, though, that there's a heavy concentration of dots close to this number and very few that are far away from this number? Does that make sense? Okay. There is actually a miniature normal distribution of those points right there. Okay. So imagine if I could take just that chimney of data and plot just that chimney of data, make like a histogram or something out of it. It would create a normal distribution, and this is heights of sons and their dad is how tall? 72 inches. So this is not a normal distribution of all the father's heights or a normal distribution of all the son's heights. This is the normal distribution of just the boys' heights when their dad is 72 inches tall. Does it make sense to you that it would be centered at our prediction? Yeah? And you know how we always go 1, 2, 3? 1, 2, 3? How big is this space right here? There it is, 2.46. So these two numbers now define a normal curve. Okay, I'm going to go back and put a 3-1 on here just so that those two decimals make sense. Doesn't really matter. So I got 72.31. If I add 2.46, then these ones are 74.77. Tell me about a boy that lands right here. Yeah, he's 1 standard deviation above that expected value for the height of a boy whose dad is 72 inches tall. Is this 1 standard deviation above average for all the boys? 1 standard deviation above average for all the boys is 72.5 inches. Do you see that? Okay. So 1 standard deviation above average for these boys is taller than that. How come? Yeah, because the dads are taller than average. So we expect the boys to be taller than average. Yeah, kind of? Okay. Add 2.46, so this is 77.23. It does ask you to draw this on your paper if you want to go ahead and be copying this in that blank space under H. Asking you to draw this. The normal curve, yeah. You should be able to fill in all of the blanks on G and H. And we'll finish H together in just a second. But go up to the point where you've drawn this in H. But there are some blanks you want to fill in. Okay, do you understand what I have up here? Do you understand this normal distribution? So if we fill in the blanks, it says, you already found the expected height for sons with a 72-inch father. It was 72.31 inches. Good. The give or take, or the error on that estimate was 2.46 inches. So we expect a normal distribution for the sun's heights centered at, with an SD of, good. And here we have drawn it. Okay, so this will always be the case. And the questions on your review, on your exam, everything will always start out with predict the height of a sun if his father is 72. So you've got that number. That is going to be the center of your normal distribution. Then it will ask you to find the RMS error, and that will be your SD, or your give and take on your normal curve. Now, the trick is remembering how to even do stuff with this normal curve. Yeah? Okay. So the question on H is actually, what percent of suns are expected to be above 72 inches tall, given that their father is 72 inches tall? So what height did we expect? 72.31. I want to know how many of the suns are going to be 72. Nope. Right here. And above. I want to know how many of the boys are going to be taller than their dad, basically. Yeah? Does it make sense that it's a little over 50? Because we expected them to be a little taller than their dad. So there's a few that are down there that are the same height as their dad. Okay? So, I don't know if you guys remember doing this, but we have two options. We have calculator and we have book. Yeah? So, on your calculator, this requires a normal CDF. Does anybody remember how to get to a normal CDF? Yeah, second bars. We go to the distribution menu. Normal CDF. So can you tell from looking at my picture what the low end is? 72. What's the high end? Good. What is the average? 72.31. And what's the SD? What did it give you? You typed something in wrong then. It should be 55%. So this gives you 0.55. So we say 55% of suns are 72 inches or greater, something like that, or taller. Okay. I see a calculator on every desk. Am I wrong? Does anybody need this in the book? Okay, I will just go over this really quick in case anybody that's watching over Zoom needs this review. If you need to do this in the book, okay, in the book we would have to do, first of all, a z-score, which this is a good review for all of you anyway, so follow along and make sure you understand this. First of all, we would find a z-score for that 72. So we would say 72 minus average divided by the SD. And that would give me a z-score of 0.13. Then I would look that up in the back of the book. So a z-score of 0.13. The closest I have to that is a 0.15. And that gives me 11.92%. Okay, but where is that? Do you guys remember when you use the back of the book and it gives you an area? If I'm trying to find from 72 and above, where is this 11.92%? Does anybody remember? From here to its matching point on that side. Okay? So what I would then do is split this right down the middle and say that all of this from the middle up, that's 50%. So this other little tiny piece over here is 11.92 divided by 2. Does that make sense to everybody? So 11.92 divided by 2. Add that to the 50%, and we get 55.96%. Okay? So you will always be able to answer these either way. If you don't have your calculator and you need to use your book, or if you've chosen to use your book versus your calculator, whatever. Either way, it's there for you. So 55% of the boys that have a dad that's 72 inches tall are 72 inches or taller. Okay? How do you feel about that? Does that seem pretty easy? Okay, can you do part I then? It says for all the sons, again with a 72-inch father, what percent are expected to be shorter than 68 inches? So if you look up here, 68 inches is like right here. So I'm trying to find shorter than 68 inches. Do you remember how to put that in your calculator? Yeah, good. We do negative 9999 up to where? 68. Same average, same SD. The nice thing is your calculators they keep that number in there for you, so you can just keep using it. So what'd you get? 4%? So it came out as 0.04? Okay. So like 3.9%? That was really ugly. Fine. So explain that to me. Why is that such a low number? Yeah. Exactly. So a 72-inch dad, so a 6-foot dad, right? The question is how many sons, if they have a 6-foot dad, how many of them would only be, 68 inches? 5, isn't it 5'10"? Because 5 foot is 60, so it's 5'8", you're right. So if the dad is 6 feet tall, do you expect his son to be 5'8" or shorter? Not really. And apparently it happens about 3.9% of the time, according to this slightly old data, but still. Yeah? Okay. And one more. If you find out that a certain son is 74 inches tall and his father is 72 inches tall, what percentile is that kid in? If you can remember how to do this, I'm going to be so happy. No, don't use your inverse norm. Your inverse norm is only used if you know the percent or the percentile and you're trying to find the height. So you're still using normal CDF, but how are you using it? Nope. That was a good guess, though. Hardest part about this is that it's exactly the same as what you just barely did. You just have to know which direction. So your mark is at what number? If I were to mark on here, would I put a mark at 72 inches or at 74 inches? 74, because this graph right here, this is representing sons' heights, right? Not fathers. All of the fathers here are 72 inches, so I'm not going to mark 72. I'm going to mark 74, which is like right here. But how do I find what percentile that is? What is percentile? So do you go up What is percentile? If I told you that my daughter's head was in the 90th percentile, what does that mean? It's above average, but 90% of people are that size or smaller. So when I ask about percentile, we're always going this direction. Yeah? So what's the low end? Negative 99999. The high end? 74. Same average in SD. And what do you get? So what does this decimal come out to be? 0.75395. So what percentile is this kid in? 75th percentile. Only 25% of the other sons that have that same height for their dads, only 25% of them will be taller than him. Yeah? How you feeling? Did it all come flooding back to you? Okay, good. I know. We'll just keep practicing so it doesn't go away. So, on those two questions on the next page, it's two different data sets, so don't try to use the same data set for both questions. The top one is talking about height comparisons between a husband and a wife. The bottom one is father and son again, but it's a slightly different data set. Okay, so just be careful. The SDs are different down there. So it's just directly asking you a question, but how much work did we have to do prior to being able to answer part H? Quite a lot, right? Okay, so on this third page on question number 1, it's not having you do, it's not specifically asking for all the steps, but it is asking you to do the same thing. In order to do any of this, in order to make the prediction, you'd have to have the regression line. In order to make the regression line, you'd have to have the slope and the y-intercept, right? And you can't find what percent are higher than a certain value until you've made the prediction for what they should be at that certain value. Okay? So, I want you to try. I know that's a big step from doing it piece by piece, but you have the step-by-step instructions doing that first problem. So I want you to try those two questions and see if you can come up with your answers. But be careful, because part A on both of them, what is that asking? What percentage of women were over 5 foot 8 inches? Does that have anything to do with the husband? No. So in that case, we are just looking at that one variable. We don't need the regression line. We don't need to make a prediction. We don't need to do anything. We just need to assume that the heights of the women were normally distributed and find how many women were over 5 foot 8 inches, which is what, 68? Okay. So if you know the average height is 63 and the SD is 2.5, can you find how many women were over 68 inches? Okay. Then on part B, you're going to have to go through and do the regression line and make a prediction and do all of that stuff. You also get to convert to inches because it gives it to you in feet. Okay? So I want you guys to try those. I know it might be a bit of a struggle. It might be a little hard, but I want you to try it on your own. And then we'll check your answers together so you know if you did it right.